Hello, this is Sean and welcome back to Having Fun Repairs. Here in a minute we're going to start a restoration on a 1948 Zenith radio. More on it in a second. Now, if you enjoy this video, then at the end please consider giving it a thumbs up. I also highly encourage communication down in the comment section. As I go along restoring this radio, I will go ahead and say I have never worked on a radio from this era. Most radios I've worked on are transistor based, that is transmitters, receivers, and transceivers with newer technology and components. Now that means that some things that I know are going to be applicable because a radio is a radio. However, because I've never worked on a tube-based radio, there are definitely going to be some things I will learn along the way. So as I go through certain material, if I misspeak or I say something incorrectly, feel free to drop comments down in the comment section. Also feel free to discuss this entire content in the comment section. That helps me and it helps everybody who views this channel. If you're new to this channel, or you like the general content of this channel, such as my STEM videos and repair videos, along with restoration videos, then please consider subscribing. I would appreciate that. And then to go ahead and get this out of the way, something I started recently was a PayPal account. The link will be in the description down below, so no obligation. But if you would like to donate to this channel, I will go ahead and say that any and all proceeds will go to either buying broken items, say from eBay or a local thrift shop or something in my community that would make good content for this channel, or will go to components for the repairs. Again, no obligation. With all that being said, let's get started. On the bench here is our radio. This is an American-made radio from around 1948 to 1949 by the Zenith Radio Corporation in Chicago, Illinois. There are 5 tubes in this radio. Hence, it's given the colloquial name All-American 5, or an abbreviation AA5. This is an AM radio that operates on the broadcast-only bandwidth, or medium wave, that's MW for short. These radio sets were designed to receive an AM broadcast signal in the medium wave band, and were manufactured in the United States from the mid-1930s until the early 1960s. This radio specifically has 6 AM circuits, as tuned circuits. The power it uses is your standard US 110, 120 volt AC, although you probably could adapt it for a DC input as well, depending on how you reconfigure some things inside the radio. Now we'll have a loudspeaker or permanent magnet dynamic loudspeaker with a coil rating of, actually we'll have to test it, but I imagine it's going to be somewhere between 4 or 8 ohms. Now the material it's made out of is actually plastic. This is not Bakelite. However, it has seen some better days, so we'll need to address it and get it cleaned up, and I've done a bit of cleaning before in the what was it, when I went over how to build a dim bulb tester, showed you the isolation transformer and the variac. I wiped it down a little bit then, but we've got a lot more work to do. I like the classic design of this radio. What was the model number on it? Let's flip it over real quick. FD810Y, and I think I called it the Peacemaker, but it's actually called the Pacemaker. If you can tell by how things are rattling around on it, I've got my work cut out for myself. This little plastic cover is going to have to either be replaced with something that's new old stock, or maybe I can find a way to form and make my own. This turning dial right here is actually physically broke in the center. We're going to have to address that. This on, or what I think is also the volume knob, feels stuck and is very hard to turn. That's something we're going to have to address. This knob right here, I believe, actually is for tuning the radio. However, if I put this dial back on, you can see that nothing is actually really moving. It feels like the string is slipping on whatever gears it's attached to. So that means that this radio is going to have to be restrung, which is going to be something that I'll have to learn, and it's probably going to be a big pain in the butt. Flipping it over, and all the dirt and debris that's coming out of it, we've got equally more work inside. On the back you can see the antenna. Wrapped inside of here is the power cord. Now let me show you something about this power cord. It is so old, it is literally crumbling in the hands. I mean, you could just hear that. That's terrible. I would not be plugging this into my wall outlet whatsoever. Fortunately, we do have what looks to be a parts number label or something in here that might come of handy. We can see our tubes inside the radio here. Hopefully they're functional and we won't have to replace them. We can see the permanent magnet speaker that's sitting right here. We can see our IF cans, and more on this later. We can see them sitting here. We see our tuner for the radio sitting right here. So everything is pretty accessible if you were just to replace some components through the top after taking off the back. However, we are going to have to remove this from the entire cabinet. And then get a better look at everything underneath as well to see if this radio's been worked on before or if it's all original, and potentially replacing quite a bit. Now, just something I noticed on this, if I can call it a data plate, which is a term I use in my career field for equipment that I work on. They typically come with a plate that gives manufacturer information, part number, stock number, and a whole bunch of other stuff. We can see a nice serial number right here, made in USA by Zenith Radio Corporation, serial number C813252. I was also able to pull some service literature from radiomuseum.org, such as this alignment guide you see right here, this schematic diagram that you see right here, and what is basically an illustrated parts breakdown that you see right here. These things are going to be very important for us in this restoration because I'm going to use them in order to know what I'm looking at inside of the radio itself. If I need to do troubleshooting, they will need to be used. As I replace components, I'll need the IPB in order to get the values. Now, these older values have markings that are not similar to the common error. So we need to understand that certain things such as MFD or another one might be MFF, I can't remember off the top of my head, what those actually represent in either the microfarad or picofarad rating. I think I said FD810Y, correct myself now, 5D810Y. And again, this is our pacemaker, or the pacemaker, was a name given to this radio. Now, like I said, I'm not too familiar with tubes. However, I am pretty familiar with transistor-based radios. Let me just go to the diagram for now. In order for us to understand what we have to get into when it comes to aligning this radio, I want to first get into a little bit of radio theory. So to start this out, a radio receiver must be able to receive something from a transmitter located somewhere else, either out in space or at a facility miles away, that's radiating a modulated signal out from a radio antenna tower. Now, what does all that mean? Well, let's first discuss what needs to be presented on the antenna side of our radio in order for us to receive an RF signal and demodulate it demodulate it, amplify it, and get it out to a permanent magnet speaker for us to actually hear the audio. As I stated, this radio receiver operates in the medium wave AM band. In Europe, that would be 526.5 kHz to 1606.5 kHz. In America, that translates to us 525 kilohertz to 1705 kilohertz is what I'll need at the antenna in order to produce audio out the speaker. One small correction, I think I said FD for the model number, the first two digits. It's actually 5D. Now, before I get into how this radio takes a modulated signal, heterodynes it, filters it, amplifies it, extracts the audio, and then amplifies that audio out to the speaker, I would like to talk about what a modulated radio frequency is, specifically AM modulated. To start out with, let's first talk about what needs to be present at the antenna, which is a modulated or amplitude modulated radio frequency. To demonstrate this, we need to define a couple things that need to be heterodyned together to create a modulated frequency. The first being a carrier frequency. On my SIGGEN, I have a frequency set up for 200 kilohertz, which I will turn on. And then on my O-scope, I need to turn channel 2 back off here for a second. On my O-scope, you should see that yellow big barred bandwidth type thing. That is essentially that 200 kilohertz frequency. Now, if I was to span out my horizontal control, you would begin to see that 200 kilohertz sine wave. This is my carrier frequency. When you tune a radio to a specific frequency on the dial, you are tuning to the carrier frequency. However, just tuning to a carrier frequency, if it's not modulated, means that there won't be anything other than static produced at the speaker. So in order to modulate a signal, you must also have an intelligence frequency, such as my voice or something generating a specific sine wave. On my SIGGEN, I'm now going to turn on a intelligence frequency. This is a 500 hertz frequency. This is something we could actually hear if I had it coming out of a speaker. So just to demonstrate that, I've got a cell phone in my hand that I am going to set to 500 hertz. And then I'm going to play that audio so you can hear it. That tone you just heard is this bottom on the O-scope purple line or sine wave that you see going across. That is that 500 hertz frequency. Again, I'm going to call it my intelligence frequency. Now, what occurs when you modulate an RF carrier with a 500 hertz frequency is you get a new type of waveform. On my signal generator, I'm going to turn on modulation, and my modulation frequency will be that 500 hertz signal. Look at how this signal now looks. In essence, for an amplitude modulated signal, the carrier frequency is varied in relation or in proportion to the message signal or the intelligent signal, such as an audio signal. As a matter of fact, if I was to bring up my intelligent signal, I could overlay it with the upper, or if I could shift it over, the lower sideband of my carrier, and you would see, even though it's just a wee bit off and I can't bring it over, that variation of my carrier frequency is the same cycle of my intelligent frequency. Now, given my intelligent frequency is 500 hertz, the bandwidth of this frequency is 2 times the highest frequency, meaning the bandwidth of this entire frequency is 1000 hertz. So essentially what needs to come into the antenna is what you see on channel 1, which is that modulated RF frequency of 200 kilohertz, carrying that intelligence frequency of 500 hertz. And then out the speaker, you would just get that 500 hertz tone as it's demodulated. Let's put this knowledge into some practical application. Looking at my alignment diagram, I see the frequency range of this radio is 535 to 1620 kilohertz. That KC represents kilocycles, but you could also say kilohertz. The other thing I want to make note of is my IF frequency, or intermediate frequency, which is 455 kilocycles, or 455 kHz, or kilohertz. Let's go back to the antenna. If I wanted to hear something come out of the speaker, then I need to select up something on my dial between 535 to 1620 kilocycles or kilohertz. I also need that signal to be modulated. That modulated signal is going to be fed from the antenna into my first tube, 12BE6, which is a converter tube, right here at pin 7. 12BE6 is a pentagrid converter making use of 7 pins in its construction. The main purpose of 12BE6 is to heterodyne our incoming modulated frequency, radio frequency, with something called our oscillator. Down here you can see our oscillator circuit. Now the main purpose of this oscillator circuit is to produce a frequency based upon what we have tuned to, either 455 kHz above or 455 kHz below what our dial is set at for the incoming signal at the antenna. Now I think our oscillator frequency in this application, without any service literature in front of me to go off of, I think our oscillator frequency is going to be 455 kHz above the frequency coming at the antenna. So what this means is if I have my dial set to 535, and if there was a radio station producing a modulated RF signal at 535 kilohertz, then my oscillator is going to produce a frequency of 990 kilohertz to feed into pin 1 of 12BE6. Now, the frequency coming in at the antenna is going to be modulated, but if you recall when I showed you the carrier frequency before modulation, the oscillator frequency is going to look like an unmodulated carrier. Both of these frequencies will be fed into 12BE6, where heterodyning will occur. When you heterodyne, you're actually going to produce 4 frequencies. Those 4 frequencies for receivers are typically considered your sum, your difference, and your 2 originals. If I was to take the summation between our 535 kilohertz modulated signal at the antenna and our 990 kilohertz oscillator frequency coming from the oscillator, I would get 1525 kHz. The difference would be our IF frequency or intermediate frequency of 455 kilohertz. And then our 2 originals are obviously the 535 modulated signal, 535 kilohertz modulated signal, and our unmodulated 990 kilohertz signal from our oscillator. Now, the one that I want to use coming out of 12BE6 is my intermediate frequency. That intermediate frequency is going to look very similar, if I was to put it on an O-scope, to the modulated frequency coming in at the antenna. It's just going to be at a lower frequency. Now, I used to give this example in the schoolhouse when I was teaching AM modulation and demodulation, but think of it like a haystack. Think of your intelligence on that frequency, modulated frequency, as a needle in a haystack. And of course you could dive into that haystack and go shifting around all the noise or all the debris to find that intelligence. But wouldn't it be easier to make it a smaller pile so I have less debris, less noise in order to find that signal? This is where we get into fidelity and also a bit of radio sensitivity. What I am then going to do is, using my first IF can, it will be tuned to my intermediate frequency, thus rejecting the sum and the 2 originals, before being fed into my 12BA6 IF tube. Now, before I get into that 12BA6 tube, I also want to show one more thing, or a couple more things. My IF should be coming out of pin 5, I believe. But we also have this pin right here. Either this one's 6 and this one is 5, or that one is 5 and this one is 6. It's hard to tell on this diagram. Yeah. So top one is 5, this side one is 6. If I follow this line and go all the way over to the right, I can see it shows up here on pin 4 of my power amplifier. More than likely that audio is going through, well, in the radios I'm familiar with, you would do it through a diode to make a DC reference, but you develop a DC voltage to make something called AGC, or automatic gain control. So that DC voltage is going to increase at the level, the greater the AC audio comes out as its amplitude increases, or as the amplitude decreases, the AGC DC voltage will decrease. But that AGC being fed back into my converter stage is to control the amplitude coming out. Hence automatic gain control. As it varies out the output, it controls the amount of gain at the input. I can also see over here on my antenna that we have capacitor C2, and at my oscillator I have capacitor C3. C2 I think is going to provide a degree of selection and tuning for our incoming frequency. So what I mean by that is it's giving us a little bit of filtering right from the antenna before going in here to reject maybe adjacent channels, sideband frequencies, or to reject something that we do not want at coming into our converter from the antenna. The oscillator is obviously going to be tuned because we need to get this oscillator to produce a frequency that is as close as possible to the 455 kilohertz, or to produce a frequency greater than the intended frequency at 455 kilohertz, plus or minus a percentage. It's probably somewhere here on the diagram what that percentage is. Well, with radios that that are common for me to work on, the IF is usually in the neighborhood of 0.005%. You can also call the oscillator the heartbeat of the radio. Without it, nothing else essentially works. Moving on, let's talk about, now that we have filtered our IF and rejected our sum and two originals, we've allowed the 455 kilohertz into 12BA6. BA6 is a pentode amplifier having a remote control grid characteristic, and is utilizing the miniature construction similar to the other tubes. It is an RF amplifier and is characterized by high transducence and low grid plate capacitance. The purpose of our IF amplifier is to take that low level intermediate frequency, which is going to be at a low amplitude, and increase the amplitude of it. More than likely, the IF amplifier here is also going to pretty the signal a bit, since we do have filtering, before being fed to our detector amplifier at 12AT6. Now, common around your IF amplifier in many radio applications will be another tunable can or tunable filter, in this case T2. Over here was T1. Again, these work in conjunction of eliminating any harmonics or any unwanted frequencies, because all I want in this section is my IF of 455 kHz. So these things will, if we need to, we'll have to adjust them in order to get our IF spot on, and that is also one of our alignments. Now we can move on to our 12AT6 detector amplifier tube. Our IF should be getting fed into this tube out of T2, that second IF can. 12AT6 is a combined high voltage amplifier. Just reading a little bit of script off of a data sheet that I pulled up for it. And is a double diode detector using the 7-pin miniature construction. It is intended to provide output voltage adequate for full power output of most beam powered tubes. Now, going off script and going from my understanding of other radios, your detector amplifier is essentially what's pulling that needle out of your smaller IF haystack, or pull out the audio from that, or intelligent signal from that intermediate frequency. So at the output, pin 7 it looks like. Let me go to the alignment diagram. And the output appears to be pin 7, but we're controlling the amplitude via pin 1, volume control knob. I might have that wrong, but either way, I'll have to go back and look a little bit more, but either way, at the output of our detector amplifier, we should now have that audio signal. Well, if you recall back to our signal generator, that audio signal, say if it was an intelligent frequency of 500 Hertz, you would now see that here versus any other frequency. And then we're going to control that audio with a volume knob because we want to control the speaker at the end. But we're going to feed that low level sine wave, audio sine wave, into our last tube in this section, because we haven't even discussed our rectifier down here. But our last tube, which is the 50L6 GT power amplifier. 50L6 GT is designed for service in the output stage of any AC/DC receivers. It delivers a high power output with high power sensitivity from low supply voltages. That's reading a little bit off of the service literature. In most radio applications, you don't take audio directly out of your detector amplifier and feed it to a speaker. It's going to be extremely low amplitude and more than likely not enough to fully drive the speaker, or it's going to sound extremely weak. Thus, you need to take the outputted audio from your detector amplifier and you need to amplify it in a power detector stage before driving your magnetic coiled speaker. It is the power amplifier, as I've stated, that drives the speaker and produces the tone that we are wanting to listen to. And in this case, whatever is coming out of the radio station. Now we have a very basic understanding of what comes into this radio, how it's changed and converted and amplified and produced out the back end. We also need to talk about another important section, and that is the power supply section. Down here at the bottom, you will see that you have your AC plug coming in, hitting 35W4 rectifier. Now this is a tube rectifier, and I believe is considered a half wave rectifier. Pulling up a data sheet, it says half wave power rectifier application. In more modern circuits, you would have 4 diodes put in circuit in a way that takes the AC and turns it into a unregulated DC voltage. And by unregulated, that doesn't mean that the DC voltage varies, although it might have a little bit of ripple. It means that what is being produced is going to either be in a range of DC voltage. It could be in a range of 35 volts or 50 volts or 100 volts, but it will have a designated range, and typically, depending on the age of the rectifier and the components used, that voltage is pretty steady. So if it produces an unregulated 35, then that voltage is probably always going to be around 35 volts. Again, it's probably going to have a little bit of ripple on it, so it's going to be a more dirty DC voltage. In a lot of modern radio applications, you would take your unregulated voltage and then you would regulate it into an operations voltage for supplying power to other components to make them function, such as your transistors and stuff in modern radios would use your regulated voltage in order to function. But in this application, we're taking going through this rectifier to produce an unregulated voltage for use of the tubes that you see listed at the top. Hence why they're also listed at the bottom. I also want to denote you have your chassis ground that's shown here. And then this little broomstick signal denotes your B minus, which is here. Typically, your unregulated voltage, DC voltage, is called your B plus. So coming out of this rectifier would be your B plus, and that is what's going to essentially power everything inside this radio. So I would like to go back and amend or clarify or correct, depending on how you want to view it, a few things that I mentioned previously. Starting off with what I meant when I stated pretty in the circuit. In a lot of radios that I've worked on, after you hit this stage in the radio, your IF stage, and you amplify, you send it through something called a buffer modulator, not buffer modulator, but buffer amp, or a noise limiter. Those devices kind of act the same. Noise limiter mostly is there to get rid of pulses from radar type equipment, but they do also serve another purpose, and that is eliminating any noise that is inducted into your IF and audio chain and hearing that noise at the speaker. And the noise that I'm talking about would come from either your DC section or your AC section. Okay. Now, I don't think 12BA6 is doing that. After spending a little bit more time on the diagram, we have this 0.047 cap here, which should be eliminating our AC line noise. We also have these two capacitors here, which are actually a ceramic disc capacitor that I think is on the back side of the on-off switch, which should also be, if I'm not mistaken, eliminating noise from our DC section. So we've got this here to get rid of that hum, AC hum. That is the 60 hertz hum that we don't want to hear at our speaker. And then we have this here to eliminate any DC noise from showing up on our audio and coming out the speaker. So hopefully that makes better sense now. Looking at this more closely, I think this is just eliminating our sum and two originals. So we're getting rid of any harmonics, including our image frequency. And an image frequency is basically taking your 455 kilohertz IF, you multiply it by 2, and that's your image frequency. An image frequency would be allowed through here if not for these tunable cavities that we have right here and here. But I think we're eliminating harmonics, our image frequency, and we are amplifying only our IF. The second thing I'd like to correct is when I mentioned AGC, talking about this line coming out here. Now, what is on the diagram is something called AVC. AGC is automatic gain control. AVC, if I'm not mistaken, is automatic voltage control. However, they are essentially the same thing. The purpose of this, as I previously stated, depends on how close our radio receiver is to the radio transmitter that is out in space somewhere, transmitting a modulated RF that is being picked up by the antenna. Now, what AGC or AVC is going to do, if I can explain it a little bit better, is say we have our volume set to something, a specific amplitude controlled by our volume control knob. Okay? And we like that amplitude of our audio is a good listening volume. However, I pick up this receiver and I physically move it closer to the transmitter wherever it's located at. Well, the incoming signal strength is now going to be a lot greater than what it was previously. Okay? And that means that if its amplitude is greater, then I would expect that the output of my converter stage would be greater, and potentially my IF, and potentially my detector. Well, if we look at this line here, we can see that it's actually fed up to the detector stage. I believe that's what's occurring here, coming tied off of pin 3. Potentially. I could be incorrect about that. Oh, sorry, not pin 7. Sorry, right here. No, I got that wrong as well. That line is coming down, showing up here. Maybe, again, I could be wrong about this, but it's potential that it's taking some of that audio out of circuit at our detector stage. Moving on, before I confuse myself even more or say something more idiotic. we have another tie point here that appears to be controlling the gain of 12BA6, and then we have our last tie point here, which appears to be controlling the gain of 12BE6, our converter. So what would occur in the radios I'm accustomed to is, and this is an ATC environment, as an aircraft got closer, it will start to saturate these circuits. Especially say if the aircraft was flying right overhead of the antennas on top of whatever tower or antenna mast that they're tied to, okay? And so as that incoming signal strength increased, simultaneously the output audio would increase, but I don't want that to occur. So as the output audio's amplitude would increase, you would have something called a detector diode, but here it appears the power amp 50L6GT is taking care of it, would sample that analog audio and convert it into a DC reference. So basically a sine wave here to DC here. And as the amplitude of our audio increased, so did the DC voltage. Now in some applications it could be a more positive DC voltage. In other applications it could be a more negative DC voltage, but we're still talking about a greater voltage. Just one is more negative and one is more positive. If I can put it that way and you can imagine it that way. Now if the aircraft was very far away, then those radios would only apply AGC, or in this case AVC, to say the IF, and it would start reverse biasing what was occurring here to control the output. And as that aircraft got closer, it would start applying the AGC voltage to say the converter stage, and now it's controlling here and it's controlling here. And as the aircraft got even more closer, it would apply that AGC or AVC to all three stages to reverse bias as much as possible to keep this amplitude over here constant. Now I don't think that's quite what is occurring here. I think the DC voltage is created and it's just constantly applied to all three of these vacuum tubes, but I could be wrong. So somebody who is more smarter than me, please put it in the comments if you can explain it in greater detail. And then the last thing I want to mention is, I said we'll have to do an alignment to ensure that our IF frequency is within whatever tolerance. I think I said 0.005% or whatever. What I meant to say is our oscillator frequency is going to have a tolerance. Now the radios I'm used to working on, that tolerance from the frequency produced by our oscillator, it was actually 0.0005%. So assuming that our oscillator is producing a frequency 450 kilohertz higher than the frequency coming in at the antenna, like I said, I don't know, it could be 450 kilohertz lower. We should be able to measure off of pin 1 here what that frequency is and kind of determine what the tolerance of that frequency is. However, the alignments for our oscillator is actually, there's really only an alignment for the IF section, okay? You do have C3 that will tune your oscillator, but I didn't see any instructions really written specifically to the oscillator. I suppose there were, injecting a signal here and changing C2 and C3, but primarily it's having you increase your amplitude out, or injecting something at your converter stage and then adjusting T1, T2 for max amplitude out. But anyways, kind of rambling. What I'm trying to say is there is an adjustment for this here, but if our oscillator is within tolerance, well then guess what? everything else would be at that same tolerance. Okay, so say that our oscillator produces a frequency 450 kilohertz higher than the operating frequency that's coming in, the modulated RF signal coming in, at a 0.0005% tolerance. Well, then my IF should also be within that same 0.0005% tolerance, etc. And again, the oscillator is really the heartbeat of the radio. If it does not function, you get nothing here. Okay? There is no heterodyning that will take place. Now, you'll probably, unless I'm wrong, still have the two originals show up, but they're going to be rejected. They won't make it through. So you would have nothing coming out at the speaker. And then say the oscillator is working, it just happens to be out of tolerance. Well, in that case, you might get something out, but what you're going to get out is not going to be necessarily your intelligent frequency riding on your IF. It'll be garbage. And so what you'll hear out this end is going to be garbage. Now, I've seen this before in the radios I've worked on where the oscillator is bad and it's drifting in and out of tolerance. And what I've actually heard over here is you'll hear bits and pieces of intelligent audio, but it would be in and out and intermingled with a lot of distortion and a lot of static. So hopefully I've explained those things a little bit better. Yeah, that should be it. So that's pretty much everything here in a nutshell. Why don't we go back to our desk and I'll start taking the radio apart. This is already probably a pretty long video. So this one's more than likely just going to be an overview of the schematics, our diagrams, etc. And then looking at several components inside the radio and seeing what all we need to replace. Okay, that was relatively easy. Just a back plate off and some things off the front, 2 screws, and she was out of the cabinet. And yes, she is absolutely filthy. Filthy, 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 filthy. My desk, everything covered, debris. Don't like it, hate it, need to clean it. Need to clean the chassis too. It is without a doubt beyond dirty. So you saw me snip the power cord. I'm going to write that on the list of things I need to replace. I'm going to have to get a replacement cord to come in here and solder in. We have one Zenith tube, silver tone. This is a 35L6 GT. I think it was swapped out from the 50L6 GT. I'm not sure if it is supposed to be swappable. I'd have to look that up. But over here is 12AT 12AT6. That's our detector amp. So it leads me to believe that this is most likely 12BA6, I think. Are there any markings on here? Markings are 312713. What's that top? 35W4. Okay, so this is actually our oh, it was way off. 35W4. This is our rectifier. It's a silver tone. Not sure if that's what was originally put into there, as it doesn't carry the Zenith marker, but that's at least correct. So we've got our power amp, our detector amp, our half-wave rectifier. So maybe this one is 12BA6. Let's check it. Now these are glass tubes, so you do need to be careful with them. Appears to have rubbed off quite a bit, but yes, this is 12BA6, so this is our IF amp. And just for the uninitiated like myself, they're keyed pretty much, so you can't put them in the wrong way. Well, presumably you shouldn't be able to put them in the wrong way, but I guess with enough force you can put pretty much anything anywhere. And that must mean that this is 12B6, which is our converter. Again, anything on this tube is since rubbed off, but it does bear the Zenith logo, so I assume that that is most likely original. Hopefully none of our tubes are bad, because if they are, that's going to put a significant delay in repairing this guy and putting it back together. Could probably get some new old stock, but I don't believe these things are dirt cheap. So yeah, power amplifier, detector amplifier, IF amplifier, and converter, rectifier. Looking over this, lots of cleaning. The diaphragm on my speaker feels just so paper thin. As a matter of fact, it's actually split right here on the edge. So that's going to sound awful, very awful. I'm going to try to clean this up a bit. Then we'll use a some type of soft epoxy or something to try to patch that. Find something to patch that. The tops of our T1 and T2, I don't know which one is which, but they don't look to be in the best shape. The lugs on this one kind of appears to be stripped out. Hopefully it is not. Either that, or hopefully we don't need to do any tune those. Now concerning, here's our control for turning the dial. This is where the dial is at. And I see somebody engraved their signature on this. Maybe somebody from the manufacturer. That's an actual signature right there. That's pretty unique. Gives you some history. But it just appears that that rope is slipping. And most likely is because this spring right here needs to be tensioned. I could probably take a couple loops out, which would put more tension on the string, and then this guy should be able to turn again. It's also super tight. Looking at the bearing inside of here, I'm not seeing any bearing grease, so perhaps some WD-40 down in there to clean it out, and then some new bearing grease would get that pretty freed up again. There's probably somebody going to say don't use WD-40, but it's more than likely what I'm going to be able to use. Or maybe some lithium grease or something. Oh, you tell me online. One of the guys I follow on YouTube who does a lot of these things, Radiorama, I'm trying to remember the channel name. I think it's Radiorama. Either way, I'll put the link in the description. He does this quite a bit, and he uses WD-40, and he says sue me. You know, he doesn't actually say that, but he's never run into any issues. Right here, this guy right here, that is our oscillator coil. I'll go ahead and tell you, if this guy breaks, we are dead in the water. I doubt I'll be able to find a replacement unless I get another one of these radios, in which case I'll just end up repairing that one or refurbishing that one and not this one. That is not something that you can necessarily repair. You could potentially replace, but probably extremely low probability for repair. Let's look at, still continuing to look. See, antennas coming in here. Got this here. These rubber gaskets are really worn out. I don't know if that's something I can replace or what's going on with it. It's pretty weird. It's definitely something to take note of. As far as the internals go, not much to it. What you have is essentially, let's see if I can rest this safely. What you have, okay, I'm on the magnet, is essentially point-to-point solder connections, which is not something you see in modern electronics. Everything's on a printed circuit board. We have a few electrolytics that will be down in this IF can here. Here's our IF can on top. Sorry, not IF can, but there will be electrolytics in this can. Looks like we have two values, both rated for 150 volts DC. One is 50 microfarad, the other one is 30 microfarad, I believe. So I'm not going to take the can off and replace the electrolytics down in it. What I'll do is I'll have to re-terminate whatever is going through those electrolytics up here with newer electrolytics. Meaning the can will stay, but things that are currently soldered to it will now be soldered to something else. Several oil filled capacitors, and I'll just go ahead and say, getting replaced. These things have served their lifespan. This one right here has definitely seen better days. That looks like it's practically imploded on the side. That's disgusting. Same with this guy here. Here goes a 0.05 microfarad. This is the one right here that's tied to ground. That's more than likely the one I need to replace with an X1Y2 safety cap. Because if this capacitor fails in a short, then we're taking essentially our mains to chassis, which means we have a hot chassis, which means we have a shock hazard. That's not something I'm willing, nor do I want to put myself in a position to experience. This guy is going to come out as well. A 600 volt 0.05 microfarad capacitor, but they're no bueno. Can't leave them in. Serve their purpose. These radial style resistors here have more than likely are probably still within tolerance. I mean, this one looks like it's, these two look like they've gotten pretty hot. May have to replace them, but we'll measure them with a voltmeter just to see how they look. And but more than likely they're going to be good. So the bottom line is we have a lot of cleaning to do, a lot of capacitors to replace. We need to address the power cord. Like I said, I'm just going to make a list and we'll start working through everything, one step at a time. So, did a bit of cleaning just off camera. A lot of bit of cleaning just off camera. Correction, a massive amount of cleaning just off camera. And I haven't even scratched the surface of how much more additional cleaning I could do. With that being said, I did get it to a point where I'm pretty happy with how much cleaning I did accomplish. So that was done. The other thing I did is I had these old bearings from where I was repairing a yard edger or weed whacker or whatever you want to call it. And I had this bearing grease that you use to pack bearings with sitting in my cabinet in one of my drawers. And I decided I'd go ahead and make use of it a bit. Just inside of here, and I'll try to get this on camera. But if you look down in here, here's the ball bearing that I was talking about. And I just packed those balls with a bit of that grease. And I've been spending the better half of 20 to 30 minutes or so just working it back and forth constantly. Any excess that came out, wiping it up, but just working it back and forth and working it back and forth. And the action on this has gotten better. It is still a bit rough, but it's not as grindy, I guess is the word I'm going to use. Anyways, moving it back and forth. I also put a tiny bit on this back end right here. Although I don't think it moves, it doesn't appear to move. So more than likely I'm going to spray inside of here when it comes time for it with a little bit of white lithium grease, maybe a touch of WD-40 back there. Haven't done anything with this power volume control other than cleaned it up, cleaned everything underneath as well. Should look a lot better now. But I did go ahead and also the diaphragm for our speaker here, impregnated it with oil. You know, like you can find for, say, a shredder. Just a tad bit, rubbing it ever so gently across the top until the diaphragm was fully impregnated. This thing felt like a wafer thin I'm no way of putting it, dried up piece of skin. I mean, I barely touched it there, just moving this around, and it cracked. And I barely touched it over here, and again the same thing, it cracked, and I'm going to have to repair that, otherwise the speaker is going to sound like complete garbage. But by impregnating it with a little bit of oil, it seems to have loosened up the fibers a bit, and then hopefully a little more over time they'll feel a little bit more looser, and it won't be as bad and thus when it starts to operate, hopefully it just won't destroy itself under use. But hopefully that little bit of oil does some good. Couldn't think of anything else to use, and based upon the material that this is, that seemed like the most appropriate thing to try to get some life back into this diaphragm before it self-destructs. Now, working that grease inside this ball bearing and working it back and forth, like I said, did loosen it up a bit. Depending on where this is at, I can actually get it to turn somewhat. Can get a little bit of play, but doesn't seem to want to do that for me right now. Obviously, because I'm currently recording. However, even if I did lubricate all that up, the main issue is 100% the spring. I mean, it is typically when you have a spring on a dial as such, the cord, because it's old, has gotten longer, but typically your spring would be more pulled out like that. This spring is fully in, so it's not providing much tension at all on this thing. As a matter of fact, when I just turned it there, you saw it flex a bit. But if I just slightly put tension on here, you can see that it wants to turn. And so even after I grease things up, as I will do eventually, that spring is still going to have to be addressed. Well, everyone, that's going to do it for this part of our restoration. There's still quite a bit more work that needs to get accomplished on this radio here. I still have to figure out a way to fix this stuck on in volume potentiometer, as well as the speaker, replacing many components, probably a lot more cleaning. Some other things that I'd like to work on as far as polishing it up, the chassis, and getting it presentable, and then maybe a modification to the radio as well to allow for an external device to send a audio signal through it. Now, that being said, if you're enjoying this content or this video, please consider giving it a thumbs up. If you're enjoying the entire content on my channel, please also consider subscribing. And as mentioned, I did throw a PayPal link down in the description. If you would like to donate, no obligation, you can do so. All that money, as mentioned, will go back to projects like this and other repair videos in order to create more content. That being said, I hope you've enjoyed what we've done. Take care. Goodbye.
Bark.